Okay, so hello my dear, I welcome you all in this series of 2-in-1 series. Okay, that means concept and practice. So the subject is continue with the subject fluid mechanics, and the part, it is a third part, viscous flow over the external surface. So my dear, if you I will discuss the part third. If you have any confusion regarding that, you can also watch the video part 1 and part 2, so that you are very comfortable for that one. Okay. Now, before I start this session, I will give you some. I want to share you with some information about the IMS features. If you are willing to join the live online program, what is the advantage? Advantage is that you get 800 plus hour in the live classes with the live interaction, theory book, exercise book. In the exercise book, there are 4,000 plus question is there, and all the questions have a different level. That means some question has level 1, some question level 2, some question level 3. Okay, level wise is there. And also you get 34 plus year question bank with a video solution, and that video is provided by the faculty, expert faculty, and so that you can very easily to understand. Okay, and also there is a 12 personalized one-to-one mentorship session and 130 online test with video solution. Okay, now if you want to that means know more information, just you book for the free consultation, click here the link in the description or call on this number. Okay, now the next one is you also join our Telegram group. What is that channel? That means Telegram channel is there, and what is the features while you joining the Telegram group? What you have to get? You get schedule for the free YouTube lecture PDF, important updates related to the seminar and webinar, and PSUs or other government notification, expert session on in the important topic like that it is going on, and daily quiz and many more. So you can join this one. Okay, now if you have very comfortable with the theory part, that means what you have to understand here, it's my humble request, please like, share and subscribe our channel. Okay, now I will start today's lecture, viscous flow over the external surface, part 3. See, we'll already discuss this Navier-Stokes equation in the part 1. Okay, we will discuss today also, no problem. This is a Navier-Stokes equation. What is the main implication of the Navier-Stokes equation? This equation is applicable for the viscous flow. Okay, this already will discuss how to growth the boundary layer. Why this is 0, why this is 0, what is the nature of above the boundary layer, below the boundary layer, already discussed in the part 2nd. And see, already discussed, if you move from leading edge, if you move from the leading edge to trailing edge, if you move from the leading, this x is equal to 0, this x is equal to 0 is your leading edge, and this x is equal to L is your trailing edge. And if you move from x equal to 0 to x is equal to L, the shear stress, wall shear stress, this is a wall shear stress, will continuously decreasing. We will already discuss in that previous lecture. Okay, now and this is for that. Today we will start from here. Let's suppose there is a velocity, there is same plate is there, now my dear. Now let's suppose there is a velocity of the flow is v1, case 1, and velocity of the fluid is u2 and u1 is there. Okay, free stream velocity. So obviously due to this vector notation, you can say that sir, v1, that means free stream velocity u1 is less than u2. That means in one case you have to move very fast, and other case you have to move very slow. So first you have to flow slow moving fluid. So slow moving fluid or fluid is a high viscosity. Both are the same nature. Slow moving, that means velocity is low, viscosity is high, like that. Velocity is high, viscosity is low. Okay, like that. Take this situation. So what is that boundary layer? The boundary layer growth, if the velocity is low, viscosity is high, the growth of the boundary layer is high. That means what is the delta value? What is the delta value? Let's suppose this is delta 1. let's suppose there is a growth of a boundary layer. Let's suppose this is delta 2. So delta, so if this is happening, so if the velocity is low, viscosity is high, the boundary layer thickness delta 1 is high, and if the velocity is high, viscosity is low, velocity is high, viscosity is low, the boundary layer thickness delta 2 will reduce. Why? See beta, this boundary layer is what? The formation of a boundary layer. The formation of a boundary layer, for what is the reason to formation of boundary layer? Momentum diffusion. Due to the momentum diffusion, the boundary layer will be formed. So, higher the boundary layer, higher is the momentum diffusion. Higher is the boundary layer, higher is the momentum diffusion. Higher is the momentum diffusion when? Who is the responsible to the momentum diffusion? Viscosity. Higher viscosity. So, higher viscosity, higher momentum diffusion. Higher viscosity, higher momentum diffusion. Higher momentum diffusion, more penetration. More penetration. Higher viscosity, higher messenger. Higher messenger, higher momentum diffusion. Higher momentum diffusion, more penetration. So, delta is large. Don't confuse with that one. Okay, don't confuse with this one, delta is large. Now, now my dear, we'll go to the next thing. See, now we have analyzed this boundary layer. So, for the analysis of a boundary layer, we require two equations. One is the continuity equation, other is the momentum equation. So, let's suppose we have to take the continuity equation and we have analyzed the boundary layer with the concept of a scale analysis or order of magnitude. By this is very simplest analysis. If you are scaling or more order of magnitude analysis, what is the notation? O, order of magnitude, O, or this one. This is the notation of order of magnitude or this one. These are the notation. So, write the continuity equation. This is a continuity equation. Okay, and this continuity, what is the assumption? The assumption is, see, during the analysis of the boundary layer, we already covered in the first and second lecture. What is the assumption? Assumption is the, what is the assumption? Incompressible and steady flow. Steady and incompressible flow. Okay, number second, 2D flow. Number third, Newtonian flow, like that. So, these are the continuity equation in the form of differential form. So, if you write, and what is the order of magnitude? Always take the parameter, what you have to find out, that parameter is maximum value. That is called order of magnitude. So, this is your u. Don't confuse me, sir. Dou, what is dou u? What is the dou u order? Just you write a numerical value. What is the numerical value here? What is the notation here? U. So, u have a maximum velocity is what? What is the maximum? What is the maximum? What is the maximum part of u? U is the maximum is u infinite. Free stream velocity. U is the maximum is free stream velocity. So, this u velocity in x direction, this v velocity in y direction. So, u velocity in x direction is how much? U infinite. So, here u infinite. X is the direction, this x. So, x maximum distance is L. So, put L here. So, these are the order of this one. Now, what is the order of v? We don't know. What is the v order? So, right, let's suppose take. This would take. So, v, the order of v is your v infinite, and the order of y. What is the y value? Maximum, y value maximum delta. Now, this summation of these two are 0. The summation of these two are 0. That means this is a plus and this is a minus, but the same magnitude. This is a plus and this is a minus, but the same magnitude. Like, let's suppose this is a plus 10, so this is a minus 10. So, plus 10 is equal to, right side is plus 10. So, both are equal. So, same order of magnitude. So, same order of magnitude. So, order of magnitude will same. From here, you can easily find v infinite. Free stream in y direction. So, v infinite is u infinite delta by L. This is very important. V infinite delta by L. Now, my dear, in this direction, y direction component velocity is very, very small. In this direction, velocity is very small as compared to this direction. Y direction velocity is very small as compared to x direction. That means the velocity of v, which is in y direction, the velocity of v, which is in y direction, is very, very less than velocity of u in the x direction. That means if this velocity is less as compared to this one, so when it is possible? When delta is very, very less than L. When delta A is very, very less than 1. That is very important assumptions in the boundary layer. See, delta may be greater than L, delta may be less than L, delta is equal to L, anything. But our analysis is bounded. We are analyze that value, the plate length is very high as compared to the boundary layer thickness. So these are the that means delta by L is very less than 1. Delta by L, this is the first validation of the boundary layer. This is the first validation of the boundary layer. That means this is the validification of the boundary layer. If you analyze the boundary layer, there is a prime assumption. That means the assumption number first is that the boundary layer thickness must be less than is length of the plate. Length of the plate. This is our first validation, and it will come up with the equation of continuity equation. And in the preceding lecture, the importance of this validation will be very greatly affected your equation in the boundary layer. That means now the time is to apply the momentum equation. What is the momentum equation? Where you have to apply the momentum equation? Momentum equation you are applying within the boundary layer. Why? Because we analyze the nature of the flow within the boundary layer. So within the boundary layer, what is that? Viscous zone. Yes, within the boundary layer, viscous zone. So if there is a viscous zone, you can apply the equation, Navier-Stokes equation. Navier-Stokes equation is the kind of a momentum equation. So what is that? These are the equations in the very compact form. This is your density into this acceleration is there. So density into acceleration is force per unit volume. So this is your density of the fluid, and these are the acceleration. This acceleration have a summation of two components. First one is the temporal, other is convective. So these are convective and temporal. So these are acceleration. So these are the change. This is your change in velocity with respect to time, and these are speed and the direction of the fluid is moving. This gives the direction, in which direction, and this is with respect to time. So if our assumption is the flow is steady, this term is 0. This term is 0. Okay, no problem. This is your pressure gradient. And why the pressure gradient is negative? Why? Because pressure is always, fluid will always flow from high pressure to low pressure like that. So the gradient is negative. Now, so this is our internal pressure gradient of the fluid. That was the change in pressure. Okay. This is your body force. And this body force is external and such as a gravity body force we have to take. And this term is a internal viscous force, that is a diffusion term. So these are the viscous term. So this is a force per unit volume due to the viscosity. This is the force per unit volume due to the mass of the fluid, weight of the fluid, a field. And this is the pressure force per unit volume due to the gradient of a pressure. And these are the net force, mass into acceleration, density into acceleration per unit volume. So there are two assumptions we already taken. If the flow over the flat plate, we are taking the case of the flat plate. So flat plate, we assume the steady flow. So the time dependency term will 0. And also we neglect the body force. So these two terms you have to neglect. If the body force is given, you can count it. But for the simplicity of the analysis, we can neglect the body force. Okay. Now, this equation, it is in a very compact differential form and a vector calculus form. Now we have to write the explicitity in the momentum equation in y direction first. Y direction, x direction. Why? Because we are only considering the 2D flow, x direction and y direction. First we have to take the y direction momentum equation. What is the y? If you split it, this term is 0. So what is that? And second thing is that you take this density divided by right side. So this is 0 and v dot del into v vector. So v dot del है. This is the v dot del. ये आपका क्या है? V dot del है. तो v dot del into v vector. So if you resolve this vector form into this differential form, so it is look like that. And see here it is y direction momentum. So v is there. So this is a y direction. Clear? Acceleration term. Now divide by rho. So divide by rho. So divide by rho. So mu by rho. Mu by rho is what? Kinematic viscosity. So there is a kinematic viscosity. Now if this is a Laplace operator. So del square v. So how to write in y direction? Del dou square v by dou x square plus dou square v by dou y square. That is okay. No. Now divided by rho. So here is 1 by minus. There is a minus. So minus 1 by rho. And this is what? Dou P by dou Y. Pressure is a function of x and y both. Pressure is the field. So here the pressure is the function of x and y. So here we will take the partial differentiation in the y direction. Okay. Now we'll write the first left hand side, then we'll write the order of magnitude of the left hand side, and then we write the order of magnitude in right hand side. First we have to take the right hand side. This you have to right hand side. So what is the right hand side? This is your right hand side. So what is the order of magnitude of u? Order of magnitude of u is u infinite. What is the order of magnitude of v? V infinite. What is the order of magnitude of dx? L. The order of magnitude of v, the order of magnitude of dou v, so v square divided by order of magnitude of y is what? Delta. Done. Now, so here put the value of v. Put the value of v here from this continuity equation. What is the v value? V infinite is your u infinite delta by L. This is a beautification of the order of magnitude concept. That you got the nature of the v infinite. So v infinite is the order of magnitude of u infinite delta by L. So v infinite. So here u as it is. What is the v infinite? V infinite is u infinite delta by L, and L is there. So L square. This is done. Order of magnitude of v square. V infinite square is u infinite square divided into delta by L whole square divided by delta. That is done. Now, if you take this one here, so what is that? This what? V infinite delta by L square. This one. The order of magnitude v is finite delta square L square by delta. Now, this delta cancel. That means the order of magnitude of this one is v infinite square delta by L square. The order of magnitude of this one is v infinite delta by L square. See the beauty. So both of this term, right hand side, both of this term have the same order of magnitude. So same order of magnitude. So what is the next concept of the order of magnitude? You don't add this one. Sir, this is a 2. If you add this one, this is 2 is infinite, 2 into u infinite square divided by delta divided by L square. No, it is not like that. Order of magnitude, we don't bother about the numerical value. Only symbolic value you have to consider. So numerical value, you don't consider the circle. This is the right side, left side, the order of magnitude is 2 into u infinite delta by L square. No, you take either of these two. Why? Because both are equal. If both are equal, you take either of any of two. So you have to take this one. Now, this is what? This is the inertia term. This is the net force, that is inertia term. So right portion, right side, what says that order of magnitude? Order of magnitude says that u infinite square delta by L square. This is the inertia term. Now, go to the right hand side. So what is the right hand side? This one, mu, this is diffusion term. This is diffusion term, diffusion of a momentum disturbance. This is your diffusion of a momentum disturbance. Why? Because there is a viscosity. So this minus 1 by rho dou P by dou Y. Great. So write this one, right hand side. If you write right hand side, kinematic viscosity dou square V by dou X square plus dou square V by dou Y square. This is a diffusion term, momentum diffusion term, diffusion of momentum disturbance minus 1 by rho dou P by dou Y. Okay. What is this is property. So this is the fluid property. So fluid property, don't write any order of magnitude. What this is, it is not change. So it is like that. Now what is dou square V? Dou square, it is square of dou, not V. So V infinite. Dou, it is X square. So L square is the order of mu. Dou square V, it is not V square. So it is V infinite. It is y square, so it is delta square. Is the order of 1 by rho. And very important thing, what is the order of magnitude of dP? Change in pressure. What is the order of magnitude of change in pressure? See, change in pressure is what? We know that change in pressure by the lots of experiment. If you do the lots of experiment, so we see that it above that, this one, the above that one. So from here, change in pressure delta P is the order of magnitude is your kinetic energy change, yani rho u infinite square per unit volume. So order of magnitude, this is from the Bernoulli equation. Order of magnitude of this change in pressure is if you neglect the horizontal pressure, This is a horizontal line. So horizontal, this is a horizontal change in potential is 0. So the summation of pressure energy plus summation of kinetic energy is equal to constant. So what is the summation of, what is the pressure energy order? Pressure energy order is a kinetic energy order. And we are applying outside. You confuse like that. Okay, sir, we are analysis within the boundary layer. Why you are taking outside? We'll discuss this thing. Okay. So delta P is the rho U infinite square. Put this value here back. Put the hair back. So put the hair back. Del rho U infinite square divided by Y order of magnitude is delta. So if you resolve this one, this is U order of U infinite by delta. This is what? This is a pressure gradient term. This is what? Pressure gradient term. Yes or not? This is a pressure gradient term. Gradient term. Okay. Now, so this is okay. Now, my dear, this is very important observation again. If you compare this order of magnitude of this order of magnitude, these are not the same. Why? Because there is a divided by L square and this is divided by delta square. Now again, since delta by L is less than 1, delta by L is less than 1, that means delta is very less than L. So delta is very less than 1, less than L, that means L is very higher than delta, so you can neglect as compared to this value. Why? Because this is a square. That means this value is very minimum as compared to this one. So you can neglect this one. So we can neglect as compared to the other. This term is neglected as compared to the other. That means very first point is that no matter what is there here, but dou square by dou x square of anything is very less than that dou square by dou y square. That means this is what? This is your plate direction. X is the plate direction, Y is the transverse direction. So axial diffusion of momentum disturbance. This is the axial diffusion of momentum disturbance. And this is your transverse diffusion of momentum disturbance. That means the first subtle concept is that while you analyze the boundary layer over the flat plate, the axial diffusion of momentum disturbance will be neglected as compared to the transverse diffusion of the momentum of disturbance. Clear? Transverse diffusion, we can, that means transverse diffusion is more and more as compared to the axial diffusion of the momentum disturbance. So you can neglect this one. These are very subtle concept. You first think like that. And when it is possible? When delta is less than L. So see, there is a very good approximation. Okay, so these are the diffusion term. Now that means only in this form only dominating part is this one, transverse diffusion. That means we have to take the two dimension x and y direction, axial direction or transverse direction. We will always consider the diffusion in the y direction, not x direction. So we have to consider this term only. So we can neglect this one. So we can neglect this one. So if you neglect it, this is your what? Viscous term. Nah? These are the viscous term. Diffusion term is the viscous term. So these are the viscous term. So what is the order of magnitude of viscous term? Mu V infinite delta square. What is the order of magnitude of the pressure gradient? U infinite square by delta. What is the order of magnitude of the inertia force, inertial term? U infinite square delta by L square. This is the very big, very important things if you analyze the order of magnitude accordingly, the equation, okay? That means, now, you have to take the, that means you have a pressure gradient, you have a viscous term and you have also the inertia term. We can neglect the body force and also steadiness term. So, if you check the ratio between the inertia force by pressure gradient, inertia term by the pressure gradient term, if you compare, which is dominating? So, what is the inertia force? U infinite square delta by L square. What is the pressure gradient term? U infinite square by delta. So, if you solve this one, this is your delta by L square. डेल्टा बाई एल का होल स्क्वायर. नाउ बेटा यू नो दैट डेल्टा बाई एल, अगेन delta by L is less than 1. That means delta by L ka whole square is very less. That means this term is a very minimum. So this term is very minimum. So this term is very minimum. That means the denominator part is maximum. So the pressure gradient term is dominating over the inertia term. This is the first observation. That means pressure gradient is dominating over the inertia term. This is the first conclusion that Y momentum equation, the inertial term are neglected as compared to the pressure gradient term. This is very important. This is very important. This is the first conclusion. That means you can neglect the inertial term as compared to the pressure gradient term. Pressure gradient is dominating. Now again we have to check the ratio of viscous term divided by pressure gradient term. So viscous term is what? Mu V infinite delta square. Pressure gradient term is what? U infinite square by delta. Put V infinite into U infinite delta by L. This you already find from the continuity equation. This is from the continuity equation. This you have to write from the continuity equation. Okay, so just you have to write and rearrange. So this is your kinematic viscosity divided by U into L, U infinite into L. Now my dear, 1 divided by U infinite L by mu. What is this one? This is your Reynolds number. This is your Reynolds number. The Reynolds number based on the which characteristic length? L. L is the what? Characteristic length of the plate. L is the characteristic length of the plate. And that length is always taken along the flow direction. Along the flow direction. That means if the plate, if this is a plate is there and this is your length and flow it is in this direction, so characteristic length is this one. If the flow it is in this direction, the characteristic length is width. So always take the flow, external flow, the characteristic length is always taken as the flow direction. So L it is in the direction of flow. So this is Reynolds number based upon L. Now my dear, see again this approximation. Delta is very less than L. Delta is very less than L. That means L is larger. L is large, Reynolds number is large. L is large, Reynolds number large. Reynolds number large, this term is low, small. If the Reynolds number large, this total term is small. If this is total, that means this is also very important analysis. For and these are the, if delta is less than L, delta is less than L, that means the Reynolds number is very high. That means which situation you have to considering it? Higher Reynolds number. Higher Reynolds number. Okay? Higher Reynolds number. So my dear, if you analyze that, so this term is, this 1 by REL is less. So 1 by REL less, that means again the pressure gradient is more. Again the pressure gradient is more. That means again, hence viscous term, again viscous term is less than the pressure gradient term. That means the pressure gradient term again dominating. So pressure gradient term you have to consider the inertia, and pressure gradient term you have to consider the viscous term. So viscous term and inertia term is a very negligible as compared to the pressure gradient term. This is the conclusion of Y momentum equation. That means the pressure gradient term dominating over the viscous and inertia term within the boundary layer. That means if you consider the momentum equation, this one, this is an inertia term and this is a viscous term. So this term are negligible as compared to this one. This term, this viscous term and this inertia term is a very minimum as compared to the pressure gradient term. So very minimum as compared to pressure gradient term. So this term negligible, that means dou P over dou Y is approximately 0. This is the first conclusion, dou P over dou Y is 0. That means pressure is not a function of Y. Pressure is not a function of Y. That means in Y direction, pressure is constant. Y direction, pressure is constant. That means, see, hence, This is very important conclusion about the y momentum equation of flow over the flat plate. What is that? Hence, variation of pressure in the direction of normal to the plate, in the direction of normal to the plate, in the direction of normal to the plate, the variation of pressure in the direction of normal to the plate or surface is negligible. Yes, see, is negligible. That means why it is what? Transverse direction. So transverse direction change in pressure is negligible. That means the pressure is all the point at a particular. That means pressure is a only function of x. Only. That means, see, pressure is a field, and this field is a function of x and y. Initially, we have to check like that. But conclusively, right, just now we have says that pressure is not a function of y. So pressure is not a function of y. So if the pressure is not a function of y, so pressure is the function of x. So pressure is the function of x. So pressure is the function of only one direction, which is in x direction. That means what is the dou p over dou x? Exactly right is to dp over dx. That means then it follows that for a given x, what they says that at a given x, the pressure in the boundary layer is equal to pressure in the free stream. This is very important. That's why I am writing here like that. Okay, sir, what is the change in pressure here? The same change in pressure here. That means we are defining the equation, we are applying the equation of a Navier-Stokes equation within the boundary layer. So within the boundary layer, what is this pressure change? This pressure change will write density into U infinite square. But density into U infinite square is outside the boundary layer. So we have to consider like that, outside from the boundary layer, that means outside from the boundary layer, at a given x, it's what pressure? Infinite. But conclusively says that pressure is not varying in a y direction at a particular x. So at a particular x, pressure is not varying. That means what is the pressure at this point 1, what is the pressure at this point 2, what is the pressure at this point 3, and what is the pressure at this point 4 at a particular x. All are same. So at this point the pressure is P infinite, at this point the pressure is P infinite, same pressure at this point, same pressure at this point, same pressure at this point at particular x. So if you define the gradient of the pressure, it is no matter you are considering inside or outside. No matter. That means follows that for a given x, the pressure in the boundary layer is exactly equal to the pressure in the free stream. That means what is the pressure 2, the same pressure at 3, the same pressure at 4, and the same pressure of the free stream, and the free stream pressure is P infinite, that means free stream pressure, that is pressure in the free stream. This is the very important conclusion. This is the very important conclusion, my dear. So what is the conclusion then? Here for the y momentum equation, these two things is very important. First, delta is much less than L. Reynolds number very large, and third dou P over dou Y is equal to 0. That means pressure is not varying. These are the conclusion. Today's lecture conclusion. Now, the next topic we are covering the y momentum equation, x momentum equation. Why? Because just now we have to conclude for the y momentum equation only. This is the y momentum equation, and for the conclusion of y momentum equation is this one. This is the conclusion of y momentum equation. Now we have to apply the x momentum equation, and we also conclude then there is a complete of the analysis of the boundary layer. Okay, so please like, subscribe my channel, IMS channel, and if you really helpful this video, please share another student so they also benefited. Okay, तो up to that आप इंतजार कीजिए लेक्चर 4 का. Thank you, bye bye.